Hello everyone, and welcome to this web lecture for the course Dynamics and Control of Mechanical Systems. In this video I will explain to you how you can complete deliverable 2 in MATLAB. In the second deliverable for the challenge, we have to first linearize the equations of motion, secondly we have to simulate them, and lastly we have to plot the results. So in front of me you see the code for deliverable 2, the empty one that you probably have as well. And this is below the code for deliverable 1, which I worked on in the previous web lecture. So the first thing that I'm going to do is to derive the linear equations of motion by using the linearize command in the DOMS toolbox. In order to derive these linear equations of motion, I need to provide it with the component struct, the nonlinear equation of motion, and a linearization point Q0. For this system, I am choosing the linearization point 0.3 meters for the displacement x2 and pi over 2 for the angle of the pendulum phi. If I again add a return command here, I will only run the linearization part of the second deliverable. So now by pressing run section, what we will see in the workspace is that there shows up a struct which is called linear equations of motion. Inside this struct we have our matrices M, D, K, KQ and Q, which describe the linear equations of motion. On top of that we have the same matrices but then symbolic expressions for them. Next we will simulate the linear equations of motion for a simulation time of, for example, 20 seconds. When simulating linear dynamics, it is very important to remember the equation that I'm now showing on the right. Namely, when we simulate linear dynamics, we don't simulate the generalized coordinates q, but instead we simulate variations around the operating point q0. And these variations we denote by q1. What does this mean for us? Well, it means that if we want an initial value q init that is equal to, for example, 0.4 meters for x2 and pi over 3 for the angle of the pendulum, then in this case we have to define q1 init as q init minus q0. Then, we have to choose values for the velocities as well. So I'm going to set those equal to 0 and I'm going to make the forces equal to 10 times the sine of t. So now all I have to do is remove this return command again and press the button for running this section. So after we've done that, we see that we get back the sim linear struct that describes now time and then the behavior, let's say, of the linear dynamics, which is described by q1 of t and dq1 of t. Then to see whether it really works, we still have to simulate it. And to save us some time, I prepared the code already. So what we are doing here is I am first using, of course, the time of the sim linear struct on the x-axis. And then I'm getting back, of course, the linear dynamics that we got. But in order to transform those back to the generalized coordinates q, I must offset it by the linearization point q0. Well, I do that for both the displacement x2 and the angle of the pendulum phi. And if I now lastly press the run section button, we will get the graphs that show us the behavior of the system that is now defined by the linear dynamics. And that brings me again to the end of this video. So thank you again for your time, and I hope to see you in the next web lecture.